Welcome to The Explainer. Today, we're diving into the absolute magic of artificial intelligence pathfinding. We're going to take a structured journey into how machines actually make decisions when they're navigating complex spaces. You know, if you've ever wondered how your favorite video game characters always find their way around, or how those mapping apps on your phone instantly calculate the best route, well, you're in the right place. We're going to break down the logic of informed search algorithms, and we'll set up a bit of a clash between different problem-solving strategies to reveal the ultimate champion. Okay, so let's start with a really relatable problem. Just imagine dropping a little robot right into the middle of a massive, super complex maze. Our robot friend has to figure out how to get to the exit, right? But how does it know which way to go? In the early days of search algorithms, strategies were mostly what we call uninformed, which basically means the robot would just wander around. It'd check every possible path systematically until it literally just stumbled upon the goal. But man, as mazes get bigger, that becomes unbelievably inefficient. So that brings us to the core challenge we're tackling today. How on earth does a machine find the optimal path without just guessing blindly or wasting precious time searching every single dead end? It needs a sense of direction, for sure. It needs what computer scientists call informed search. And to really grasp that, we need to introduce our first major concept. Section 1, the magic compass, understanding heuristics. To solve this whole massive maze problem, we essentially give our robot a magic compass, which in computer science terms is called a heuristic. Just as a quick refresher, a heuristic is really just a function that estimates how close a given state is to a goal. It's not a perfect measurement of the exact path, mind you, but more of a calculated guess based on the information it has right at that moment. Like if you're using a map, a heuristic might be the straight line distance between where you are and where you want to go, completely ignoring pesky things like roads and buildings. It just gives the algorithm a really good hint about which direction is probably the best one to explore next. Think of it like an internal meter, a sort of heuristatron gauge estimating the robot's proximity to the finish line. When the robot moves closer to its target, that gauge shoots up toward goal. This heuristic estimate guides the search, constantly pulling the algorithm closer and closer to the prize. But, as we're about to see, relying entirely on just this one gauge can absolutely get you into some trouble. Section 2. The impatient explorer. Greedy search. And that brings us to our first, somewhat flawed algorithmic character, greedy search. Picture a little drilling robot trying to reach a diamond. Greedy search operates under a very, very simple strategy. It always expands the node that it thinks is closest to the goal, based entirely on that heuristic compass. It literally just looks straight ahead. Now, in a best-case scenario, this takes you straight to the goal extremely fast. But in reality, by digging straight down toward the prize, it completely ignores the solid rock and potential traps right in its way. In the worst-case scenario, greedy search is basically like a badly guided depth-first search. It can lead you straight into a dead end, forcing a massive, incredibly costly backtrack. Sure, it's fast, but it is terribly short-sighted. Section 3. The calculated strategist, A-star search. So, we clearly need a better hero here, and that is A-star's search. Contrasting these two opposite approaches really highlights exactly why A-star is so brilliant. On one side, we have our impatient greedy search, which only looks forward at the estimated distance to the goal. We call this forward cost H. On the flip side, we have uniform cost search. Now, uniform cost is incredibly cautious. It only orders its path by the actual cost it has already spent to get there, the backward cost, which we call G. Uniform cost is guaranteed to find the shortest path, absolutely, but it is so slow because it ignores the goal entirely and just explores everywhere. So, here is the crucial breakthrough. A-star perfectly balances these two extremes with one incredibly simple formula. It calculates its next move based on F, which is the total cost, and it finds that total cost by adding G, the cost already spent, with H, the estimated effort remaining. By combining the backward cost and the forward estimate, A-star is both optimal like uniform cost search and highly directed like greedy search. It really is the ultimate pathfinding formula. To kind of see how this builds, imagine a heat map on a Pac-Man maze representing uniform cost search. You'd see a search contour expanding equally in every single direction from the starting point. It's expanding blindly, completely ignoring the fact that the goal might be all the way on the bottom left. Yes, it will definitely find the absolute best path eventually, but it wastes a massive amount of time and computing power searching in the complete opposite direction first. Now, contrast that with greedy search. Here, you'd see the search making a massive, narrow beeline straight toward the wall closest to the goal. It completely ignores everything behind it. But the catch is, it hits a wall, and then it has to snake its way through a suboptimal path to recover. It found a path very quickly, sure, but it is definitely not the shortest or most efficient one. And finally, we have the A-star search approach. This is the absolute sweet spot. It mainly expands toward the goal thanks to the heuristic pulling it forward, but it also widens out just a little bit at the intersections. It hedges its bets. By constantly checking the total cost, remember that's past effort plus future estimate, it ensures it never misses a potentially better shortcut. It guarantees it finds the absolute optimal path without having to explore the entire board. Section 4. The Golden Rule. Admissibility. But, of course, there's a catch. For A-star to guarantee that perfect path, our heuristic compass cannot be flawed. It has to follow a very strict mathematical rule. H of n must be less than or equal to H star of n. What does that actually mean in plain English? Well, the H is our heuristic estimate, and the H star with the little asterisk is the true actual cost to reach the nearest goal. Your estimated cost must always, always be less than or equal to the true cost. We really have to emphasize this golden rule of admissibility. Your heuristic must be optimistic. It can never over-exaggerate the difficulty of the path ahead. And why is that? Because if your algorithm thinks a really good path is actually incredibly expensive, it just won't even try it. It'll settle for a worse path simply because it mistakenly thought the good one was way too hard. Finding good, cheap, optimistic heuristics is literally the absolute key to making A-star search succeed. Section 5. Remembering the past. Tree versus graph search. Now, even with a perfect heuristic, there is a massive pitfall our algorithm might face, and that's memory. The danger of repeated states is a very real thing. Just imagine a confused robot stumbling across its very own footprints. If your search algorithm doesn't remember where it's already been, it can easily end up walking in endless circles. In really complex spaces, failing to detect these repeated states can cause your computer to do exponentially more work for no reason. Which brings us right to the critical difference between tree search and graph search. A basic tree search just keeps branching out. This creates a ton of extra work because it will happily re-explore the exact same state over and over again if it approaches it from a different direction. Graph search totally fixes this. It simply keeps a memory bank, called a closed set. Before expanding a node, it checks that closed set. If it's been there before, it skips it. If it's new, it adds it to the set and explores. This simple little memory trick saves a tremendous amount of processing time, though it does require a slightly stricter rule for our heuristic, something called consistency, to maintain perfect optimality. Section 6. A-star in the real world. So, we've looked at the math, the mazes, and the memory, but here is why this actually matters in your everyday life. A-star is quite literally the invisible engine powering our modern world. It is heavily used in video games for character pathing. It's the core of routing problems, meaning every single time your map app finds the quickest way to the grocery store while avoiding traffic, it's utilizing these exact concepts. It's used in resource planning, robot motion planning in automated warehouses, and even in super complex language analysis, machine translation, and speech recognition. Believe it or not, finding the optimal sequence of words is, mathematically speaking, very similar to finding the optimal path through a maze. For instance, if you look at a video game like StarCraft, there are these complex pathfinding grids working constantly under the hood. AI uses these exact search spaces to manage chaotic, real-time resource routing. When you have dozens of units moving simultaneously without getting stuck on each other or the terrain, that is A-star and graph search working flawlessly in real time, calculating costs and heuristics literally thousands of times a second. It's wild. It is truly remarkable how a simple formula, past effort plus estimated future cost, can solve such a vast array of incredibly complex problems. So the next time your GPS seamlessly reroutes you around a nasty traffic jam or a video game character perfectly dodges an obstacle, will you recognize the invisible math finding your optimal path? I really hope this explainer has given you a newfound appreciation for the algorithmic heroes running quietly in the background of our daily lives. Thanks so much for learning with us, and keep exploring.